This is module 2 of chapter 1. This module is devoted to the solution of simultaneous differential equation of first order and first degree. This type of equations has applications in mathematical physics, and in this module we shall solve, or rather we will discuss different methods for solving the simultaneous equations, and later on we shall discuss how to use the concept of solving simultaneous differential equation to solve a geometrical problem. In this module we shall mainly discuss how to solve a simultaneous equations in 3 variables. The general representation of a simultaneous equation in 3 variables is this: P1 dx plus Q1 dy plus R1 dz equals to 0, and the similar equation is given here, where each Pi, Qi, Ri are functions of x, y and z. There is another way to represent this equation as follows. From these two equations we can write the equation in this form: dx by this equals to dy by this equals to dz by this, or dx by p equals to dy by q equals to dz by r, where each of p, q and r are functions of x, y and z. Therefore, the simultaneous equation can be represented in two ways. This is one way and this is another way. Now, before solving a simultaneous equation, we have to know about the existence and uniqueness theorem. It tells about whether a system of equations or simultaneous equation will have a solution or not. Suppose the function f, which is function of x, y, z, and the function g be defined and continuous in some region mod x minus a less than k, mod y minus b less than l and mod z minus c less than m, where a, b, c and k, l, m are constants and satisfy the Lipschitz condition, which are written in equation number 2. The first one is the Lipschitz condition to the function f with respect to the variable y and z, and the second one is the Lipschitz condition to the function g with respect to the variable y and z. So, if these two conditions are satisfied, and here these ai and bi's are some finite constant. So, if this Lipschitz condition is satisfied, then the given system of equations, that means the equation dy dx equals to f x y z or dz dx equals to g x y z has some solution which is continuous and having continuous derivatives in a suitable interval mod of x minus a less than h, and this solution also satisfies the bound initial condition y at a equals to b and z a equals to c. So, this is an important theorem regarding the existence of a simultaneous differential equation. So, if these conditions are satisfied, then only simultaneous equation has some solution. Now, we shall discuss different methods for finding solution of simultaneous equation. Now, if we go back to the representation 1 of the simultaneous equation, if you take the first two equation dx by p equals to dy by q, suppose this equation is solvable, then we will get a relation of this form: u1 xyz equals to C1. Now, if we take the second and third equation, that means dy by q equals to dz by r, then we will get another relation u2 xyz equals to C2. And we have already read that a function u1 xyz equals to C1 represent equation of a surface, and u2 xyz equals to C2 represent equation of another surface, but these two equations together represent equation of a curve. Therefore, equation 4 represent a system of curve with two parameters, and those two parameters are C1 and C2. So, here we learn that the simultaneous equation in three variables, the general solution of this type of equation is a system of curves with two arbitrary parameters. Now, we are going to discuss how to find the integral curve of a given equation. So, in method 1, so we are basically want to find a surface u1 xyz equals to C1. So, how can we find u1 that we want to describe? Now, any tangential direction through the point xyz to the above surface will satisfy the relation du1 equals to, this is the total derivative of u1, equals to 0, del u1 del x dx plus del u1 dy dy del u1 del z dz equals to 0, and we have the equation dx by p equals to dy by q equals to dz by r. Therefore, these dx, dy, dz, they are proportional to the function p, q and r. Now, if you assume that del u1 del x as the function p dash and del u1 del y as the function q dash and del u1 del z as the function r dash, then this equation becomes pp dash plus q, q dash plus r dash equals to 0. So, our aim is to find p dash, q dash, r dash such that the equation 5 holds, and at the same time this d1, that means p dash dx plus q dash dy plus r dash dz must be an exact differential. Therefore, our aim is to find p dash, q dash, r dash which satisfy this equation, and this is an exact differential. Now, we shall take one example, then it will be more clear. Suppose we have to find integral curves of this simultaneous equation. So, for this equation, p is xy minus z, q is yz minus x and r is 1 minus z square, and we choose p dash, q dash, r dash in such a way that p dash plus q dash plus r dash equals to 0, and these p dash, q dash, r dash are such that p dash dx and q dash dy plus r dash dz, this must be an exact differential. So, with this choice of p dash, q dash, r dash, it becomes exact differential, and that is written here. So, for this equation we get one integral curve u1 equals to x plus y into z plus 1. Now, to find the general solution of this equation, we need two integral curves. So, we again choose three functions p double dash, q double dash, r double dash in this way, and we also see that it satisfies this relation p double dash, q double dash plus r double dash equals to 0. Not only that, it satisfies also this quantity with this choice of p dash, q dash, r dash, this quantity becomes exact differential. So, our next the second integral is u2 equals to x minus y into z minus c. Therefore, the general solution of the system given system of equations can be written in this form. So, this is one integral and this is another integral, and these two equations represent equation of a curve with two parameters. Now, we shall describe another method to find integral. In the previous method, we have chosen p dash q dash r dash p double dash q double dash r double dash arbitrary, or in other words we can say that with using trial and error method we found the expressions for p dash q dash r dash and p double dash q double dash r double dash. But if we want to find the values, the expressions for these variables mathematically, we have some derivation. Now, this is our given equation. Now, this is equals to p double dash p dash this, q dash dy r dash dz by this, and this is also equals to this. Now, we have to choose p dash q dash r dash in such a way that it becomes total differential or exact differential. So, let this is dw dash and this is dw double dash. So, if we equate these two quantity, then we will get a relation between the two integral w dash equals to w double dash plus c. So, using this method we can find the integral curves. Now, let us take this example. Using method 2, you want to find integral curves of this equation. So, this is our p, this is our q and this is our z, and in this equation alpha, beta, gamma are constants. Now we multiply the numerator with lambda, d lambda into dx, we compute this mu into dy, nu into dz divided by this. Now, we want to find the values of lambda, mu, nu such that each of the expression. Now, we shall take one example to explain the method 2. We have to find integral curves of this equation. In this equation alpha, beta, gamma are constants. Now, in method 2 we try to write the equation in this form: lambda dx plus mu dy nu dz divided by lambda into y plus alpha z plus mu into z plus beta x plus nu into x plus nu y. Here lambda, mu, nu they are constant and we do not know the values of lambda, mu, nu, and we want this expression is to be exact differential. That means this expression can be written in the form 1 by rho lambda dx plus mu dy plus nu dz divided by lambda x plus mu y plus nu z. Now, these two equations, the previous expression and this expression, will be equal or equivalent if and only if in the numerator these two expressions are same, but in the denominator to make the equivalent relation we have the coefficients of x, that means beta mu plus nu must be proportional to lambda rho, that means beta mu equals to plus nu equals to lambda rho, and similarly equating the coefficients of y from the denominator we will get other two equations. Now, to find the non-zero values of lambda, mu, nu, we have the condition the determinant of this matrix must be equals to 0. So, that will give a cubic equation in rho in terms where the coefficients are written in terms of alpha, beta, gamma, and solving this equation we will get 3 values of rho, and let us suppose that those 3 roots are rho 1, rho 2 and rho 3. Therefore, in the previous expression each of these quantity can be written in this form. That means the given equation are proportional to this value. That means here we are taking the value rho as rho 1 and here we are taking the value rho as rho 2 and here we are taking the value rho of rho 3 and the corresponding values of lambda, mu and nu are considered, and these three expressions are same. So, equating those expression we will get this relation. If we equate first two equation we will get an equation of this form, and the third there will be a third relation corresponding to rho equals to rho 3 and lambda 3, mu 3, nu 3. So, equating the first one and third one we will get a equation of a surface like this. Thus, we get two integrals of the given equation. So, in this way using method 2 we can solve the given equation. Now, we are going to describe method 3 which is most simplest. In this case we are assuming that one of the variable say z is absent from one equation of the set. That means, in the equation dx by p equals to dy by q equals to dz by r, in this equation z is absent. So, dy dx is q by p, but there is no any z. So, we can solve it. This is a first order differential equation. So, we can solve it easily and let that solution is f x y c 1 equals to 0. Now, from this expression eliminating x or writing y as function of x and substituting that in the original equation, we can get the other integral. Now, we will explain that method taking this example. We have to find the integral of this equation. So, if you see this equation, you can see that if we take the second and third one, you can eliminate the function x from these two equation. So, if we eliminate x from the second and third equation, that will give equation dy dz equals to y by z, or in other words we can find the solution as y is equal to c1 z, where c1 is the integrating constant. Now, using this form of y, if we substitute in the first equation the functional form of y or the value of y, if we substitute here, we will get a relation like this where c1 is arbitrary constant. Now, this equation first and third equation, this will give a equation which is solvable, and integrating this equation we will get another integral which is written here x square plus y square plus z square equals to c2z. Therefore, there are two integral of the given equation, one is y is equal to c1z and the other one is x square plus y square plus z square equals to c2z. So, in this way we can solve the simultaneous equation using method 3. Now, we shall discuss how the method of solving simultaneous equation can be applied in geometrical problem. In the geometrical problem, we shall show that how to find orthogonal trajectories of a system of orthogonal curves. Now, we shall discuss how to find orthogonal trajectories of a system of curves on a given surface. Suppose the equation of a surface is given by equation number 7, f x y z equals to 0, and there is a system of curves on this surface, and let the equation of the curve is given by together with equation 7 and equation 8. Since in equation 8 there is one parameter c, so 7 and 8 together represent a system of curves where for different values of c we will get different curves. So, c is a parameter in this equation. Now, we are interested to find the orthogonal set of curves to this curve system of curves and which also lie on the surface 7. For example, let us take a cone. The equation of this cone is given by x square plus y square equals to z square tan square alpha. Now, if we cut this plane by the plane z equals to c, then different values of c we will get a curve. For this case, this is a system of circles. So, we are interested to find a system of curves which are perpendicular to all these circles. So, for this case, they are nothing but the generator of this cone. Now, how to find mathematically orthogonal trajectories of a system of curves is described in the next slide. Now, we know that dx, dy, dz represent the tangential direction to a given curve, and the equation of the curve we already know is represented by equation 7 and equation 8. Therefore, the tangential direction to the curve will satisfy these two relations, del f del x dx plus del f del y dy plus del f del z dz equals to 0, and a similar equation for g. Now, if we solve these two equations, we will get a simultaneous equation like this, where p, q, r, they are function of del f del x, del f del y, del f del z, and del g del x, del g del y, del g del z, and these expressions are written here. So, these are the Jacobians of the function f g with respect to the variables x y, z x and x y z. Now, we want a direction dx dash dy dash dz dash such that it is perpendicular to dx, dy, dz, and at the same time it lies on the surface f. So, the curve through x y z of the orthogonal system has the tangential direction dx dash dy dash dz dash, then it will satisfy the equation del f del x dx dash plus del f del y dy dash plus del f del z dz dash equals to 0, since the orthogonal systems also lies on the surface f and it is perpendicular to the original curve. That means dx dx dash dy dy dash dz dz dash must be equals to 0, and dx dy dz they are proportional to p q r. So, we arrive to the equation number 11. Now, we have to solve for dx dash dy dash dz dash, and these dx dash dy dash z dash are given by equation 10 and 11, and solving 10 and 11 we can write the simultaneous equation in this form, where expressions for p dash, q dash, r dash are written in equation number 13. Now, this equation we have to solve the equation number 12, that will give the system of orthogonal trajectories. Now, we shall take one example to visualize the thing more clearly. Suppose we have a surface x square plus y square plus 2f yz plus d equals to 0, and the system of curves are represented by this surface and the intersection of this surface with the xy plane. That means, the equation of the system of curves is represented by z equals to k and this surface, that means x square plus y square plus 2f yz plus d equals to 0. Now, if dx dy dz is the tangential direction to the surface, or better say to the curve, then it will satisfy the equation x dx plus y plus fz dy plus fy dz equals to 0, and also dz equals to 0. Now, solving these two equations we will get this relation, this is a simultaneous equation in 3 variables, and now we want to find a direction which is orthogonal to this direction. So, that direction, if that direction is dx, dy, dz, so this will satisfy this equation, since the orthogonal trajectories must lie on the given surface. So, this equation will be satisfied and the orthogonal trajectories is perpendicular to the given system of curves. So, this equation will be satisfied. So, if we solve these two equations, then that will give the differential equation for the orthogonal trajectories. Now, we solve this simultaneous equation using the method, different methods which we have described already. We will get the solution like this. So, this is one solution, and this gives the orthogonal trajectories together with the equation of the surface, which is written here. So, the system of orthogonal trajectories is given by this equation and the integral of this curve, that means this equation f y z plus d equals to c x. Thus, the solution of the given equation is given by f y z plus d equals to c x, which is integral of this equation and the equation of the surface x square plus y square plus 2 f y z plus d equals to 0. Thus, in brief, we learned how to find solution of a simultaneous equation of first order first degree. We have learned 3 different methods to solve those equations, and we have also learned how to find orthogonal trajectories of a system of given curves. This ends the module 2 of chapter 1.